do the Python code for the linear elasticity problem with quadrilateral elements. Before I begin though, reminder, if you haven't looked at the previous lecture, I would recommend actually lecture 24. I solved by hand a problem with the triangular elements with a constant strain triangle, and I also uploaded code for that. So there is code on the Python folder that covers the solution of a very, very simple linear elasticity problem with two triangular elements, but like you've probably seen, all you need is the basic structure, and then it can generalize pretty well to bigger meshes. So if you haven't checked that out, then I would suggest go through the lecture materials, the slides for the solution with the constant strain triangle, and then look at the code for the constant strain triangle. And what I'm gonna do in class right now is gonna be the quadrilateral elements. So I'm going to do the linear elasticity problem with quadrilateral elements. I have a couple of slides. Strong form to weak form, that doesn't depend on whether you have quadrilateral or triangular elements, that's just the same. And this is just brief reminder. Then discretization in 2D. Here it doesn't really matter, it looks the same basically for whatever elements you have. You have sum of shape functions times null values for x and y displacements. So that stays the same. What is different is that for quadrilaterals you will have 4 shape functions as opposed to 3 that you had for triangles. But this notation is pretty much the same. You're going to have a sum of shape functions times null values. The B matrix that I introduced, which has the gradients of the displacements, or basically the strains, it also stays the same. So if you remember, I wrote this a few lectures ago. Basically, you have 3 rows and then twice as many columns as number of nodes per element. So you have, for example, derivative of n1 with respect to x, 0, derivative of n2 with respect to x, 0, and so on. Then 0, derivative of n1 with respect to y, 0, etc. And then sort of the cross derivatives for the shear strain. And this looks the same for any element, with the difference that, for example, for the triangular elements, we had only a 3x6 matrix because we had only 3 nodes, therefore 3 shape functions. Therefore, this is always twice the number of nodes per element, so this would have been 6. And then in the quadrilateral case, the structure is the same. It's just going to be a 3x8 matrix because now we have 4 nodes for the linear quadrilateral, which means that we need twice as many columns. There's one thing that is going to be different with respect to the triangle, and that is that for the triangular element, I had the shape functions directly in terms of x and y, so I could take these derivatives easily. I didn't really have to do anything. I just took the derivative. And the other thing is that because the shape functions were linear over the element, we didn't really need to do any integration, and so we really didn't need to use any sort of quadrature rule. But for the quadrilaterals, we do, and that entails one basic problem is that we cannot easily define the shape functions in terms of xy, and what we will have is we will have the shape functions in terms of the parent domain coordinates xi and eta. So in order to get derivatives with respect to x and y, what you need to do is you need to use the inverse of the Jacobian. So you need to build the Jacobian matrix, and this is the Jacobian of the isoparametric map. And then you can use the inverse of the Jacobian times derivatives with respect to the xi and eta variables to get derivatives with respect to x and y. So that's one thing that is going to be a little bit different from the triangle. So in the triangle, I was able to assemble the B matrix straight away because I had the shape functions in terms of x and y. In this case, I have the shape functions in terms of xi and eta. And so I need to build the Jacobian, take derivatives with respect to xi and eta, and then use the inverse of the Jacobian to get derivatives with respect to x and y. So that's going to be a little bit different. Anyways, Once you have the derivatives of x and y, and you can put them into the B matrix, then the definition of the stiffness matrix is exactly the same. So the definition of the stiffness matrix is the integral of the B transpose times D times B matrix. And for doing this integral, because we have everything in terms of psi and eta, then we can use the standard Gauss quadrature rules. And you have actually done some integration in the quadrilateral. So, you can reuse basically the code that you have used for integration over the quadrilateral. And then for the forces, same as before, you just need to integrate the shape functions times the body force vector over the quadrilateral. And again, because you have the shape functions and everything in terms of psi and eta, you can just use Gauss quadrature. Now, I'm not going to do an example with boundary tractions because this gets a little bit trickier because you have to do the integral on the edge. So that might be a little bit tricky, so I'm not going to do this. And then once you have the stiffness matrix and the force vectors per element, you can put them into the global system of equations and do the partition as usual and get the solution. So for this lab, the problem that we are dealing with is we have this quadrilateral mesh, and then we have a centrifugal force, which is given in terms of x and y. So omega squared times the vector x and y, where omega is just a constant angular velocity of 100 radians per second. And then the inner boundary has essential boundary conditions. And that's it. So there's no traction, I guess. All of the outer boundary has traction boundary conditions or force boundary conditions, but they are zero. So we don't, this integral right here, the force vector due to boundary attractions is just going to be zero, so we don't have to worry about that. So really, we only have to worry about the force vector, which is going to be given by this centrifugal force and this stiffness matrix. That's it. So this is the problem that I'm going to solve, and starting in the next video.